Hope everyone's having a good night. We're almost done. Anyway, we're Team Lead, and my name is Matthew Goldfinger, and I'll be presenting tonight along with Taylor Myers and Ian Hall. And our project, just very quickly, is concentrated photovoltaic systems, and we'll describe what that is a little more. So just a quick presentation overview, what we'll be discussing. So number one, we want to explain the situation, the world situation that we're trying to deal with, the problem, so to speak, that we're trying to combat, and exactly the questions we have to ask about them. And then to justify the route we are taking to answer our question, and then go on to explain our methodology. And then, because you guys are going to be embarking on this process shortly, a lot of freshmen in the room, explain pretty much what we've learned from this process and what we think you guys should be doing. All right, so obviously there is an energy crisis and we have environmental concerns at this point. And green technology is kind of the buzzword. A lot of people are working on many different types of projects. And one of the major things that people are looking at are photovoltaic cells, your solar panels. And while it is a green technology, there are various issues associated with this technology. And some of them are the manufacturing cost, both in terms of carbon output. It is not a carbon neutral processing, and the actual monetary cost. Additionally, the problem is that they are low efficiency. Some solar panels can get up to a 20% efficiency of light coming in, but some of them are far lower. And so that low efficiency is something that we want to look into. And so one of the proposed ideas on how to improve both the cost benefit of using solar panels and to improve the efficiency is a concentrator system whereby lenses or mirrors are used to focus light specifically on these panels. And so we're looking at this, and while this technology has pretty much been used on a large utility scale, it has not really been extended down to a consumer level, something you can throw up on your roof to at least take some of the power from the sun instead of the grid. And so, again, these are too costly except on a large scale. So we wanted to look if there was any way to make it something that you could put on your roof. So our research questions, therefore, to what extent can these low-scale concentrated photovoltaic, or CPV, to what degree can they be used, and how do they compare to the status quo, the flat panels you'll see on people's roofs, the flat panels that don't have any concentrator, and then how would they compare in terms of output and cost? And then also, to what extent will, one problem we've been realizing is over the year, the sun's trajectory, the sun's arc across the sky varies. And with a concentrator, how will that handle the variation inherent in the day and in the year? And so our answer is, and our hypothesis is, that we believe that our system, which will be described shortly, will be an effective substitute and will, without increasing the startup cost significantly, improve the efficiency and allow you to get the same power output by using fewer cells which have the problems I previously described. So again, just the lower cost of our system will be one key thing. Why exactly we're using the materials we're using? It's the fact that we're using low-cost things that you can find at a hardware store. They're easily manufactured. Many of them are recyclable, and you can pick them up at a local Home Depot or gardening shop. And this is what we built a reflector out of. Whereas other people use lenses and things that are very expensive, very temperamental, and require a high degree of maintenance, we've used things that will be easy to procure, not very expensive. It can be hopefully, we're going to be testing to see if using these low-grade materials, we can still get a high degree of efficiency without increasing costs very much. And so hopefully the end result will be able to get the same amount of power output from fewer solar cells. All right, so I'm going to be passing it off. The reflector design will be described by Taylor.
Hi, like Matt said, I'm Taylor. I'm going to be talking to you about our reflector design. This is not our reflector. We kind of wish it was our reflector. That's really cool of you. But we're using something similar. It's a linear focus parabolic reflector. which means it's basically a big, long, parabolic trough. The light comes in, is reflected off of it, and is focused in a long line. In our case, that long line is going to be focused on the photovoltaic cells. Normally, this is used for things like solar thermal. It's kind of difficult to do it on photovoltaic cells because photovoltaic cells are very sensitive to varying amounts of light. They only tend to generate energy about the lowest, at the portion of lowest light, which is why shading is a big issue for photovoltaic cells. They're often put in bright, sunny areas. Now, our design is based on a program written by our mentor. It takes incident rays of light at a given angle, that's the dotted lines you see up there, and generates a curve, the blue lines, to reflect light, once again, onto the little black cell, which is going to be our photo cell. It optimizes using Newton's method, which is a zeroing approximation, and it varies based on the angle of the sun. So if we were to change the angle of the sun, we'd get a different ideal curve. This is what our actual reflector is going to look like. This is our fixed reflector design. As you can see, it has two portions. That's because we're using a bifacial design. We have a solar cell on either side of the little black thing you see there. And how this is constructed, it consists of about 4 parts. The first is the frame. That's the brown wood you see all around. That's holding up everything. Then on top of that, there are ribs, which are constructed to the shape of the curves that we specified in the program earlier. On top of that is a flexible piece of wood. And on top of that is a shiny piece of mylar, which is basically a very reflective piece of plastic. Light comes down, reflects off of it, and onto our panel. The mylar isn't perfectly reflective, and our curves aren't perfect in construction, but we believe that they're good enough that we should be able to get some strong concentration out of it. Now, we've been working to construct this, and as we were working on construction, we came across some issues with weathering. We noticed that some of the sample solar panels that we put up there tended to warp and bend, so we decided that we were going to have to test this first. So we went to the shop and we started to put things together, and as we were demoing this and putting together the masonry, that's the flexible board, and the mylar, we realized that there was another way that we might be able to make the reflector. And so we're also testing a flexible reflector design. Something important to understand is that any 3 points can determine a unique parabola. So if we can specify 3 points, either through fixing the edges or fixing an angle that something is coming in, we can generate a unique parabola. Our optimal reflector shape can also be approximated by a parabola. So by varying this shape, we can generate multiple parabolas, as opposed to with our fixed design, where there's only one curve. This is useful because, as we talked about, the sun moves in different heights across the sky across the year, so the incident angle of the sunlight is different throughout the year. With our flexible design, we get more flexibility out of our design. We're more able to adjust to incoming light and adjust to changing environmental conditions. So here we have some pictures of our construction. So far, that's our demo reflector that is using the flexible design. We have some pictures of us constructing the actual reflector, which is on the next slide. And you can see it's pretty big. It's about 6 feet long. It's going to be reflecting on 1 feet of solar panels. It's very wide. Each of the curves is about 1 meter in length.
Do you want to switch to the lapel mic?
I can try. How do we turn it on?
There's a little switch right on the top of the black box.
Does this work? Wow. I stole it. So here's some more pictures of our construction. The arc length of our actual curves that the reflector is on are close to 1 meter. Our solar cells are only about 3 inches wide. If you think about the fact that all of the sunlight that's reflected on those curves should be reflected back onto our solar cells, that's a concentration ratio of almost 10. Now, we don't think we're going to get concentration quite that high, just because there are inaccuracies in our construction and there are problems with the reflection of the mylar. But if we get anything close to that, we'll have a very, very strong concentration for very cheap. The reflector does not cost much more than the solar cells. At this point, I'm going to turn it over to Ian, who will talk to you about our actual solar cells.
Hello. Hi, I'm Ian. I'm going to be talking about the solar cells we use in our project. First, to give a brief rundown of how photovoltaic cells work. Incident photons of light strike the top of a solar cell, exciting electrons in the upper layer. This creates a current and generates a potential across the cell. We can then run this voltage across resistance, outputting power. There are three main types of cells. We have monocrystalline, polycrystalline, and thin